Very glad to have Raswan Gurau here today. He will speak about random tensors. So if there's any questions, as usual, Raswan, should we interrupt you or?
Yes, so please interrupt me.
Okay,
Don't
great.
raise hands and stuff like that because I can't really see anything. So just, I made the presentation full screen. So just, don't hesitate to interrupt. And, hi everybody. So I'm Rasman. So today I'll be telling you, I'll be giving a brief introduction to random tensors. And this is supposed to be not very technical introduction. So please don't hesitate to interrupt. I mean, there's a point to interrupt, maybe to clarify some points. The talk today is divided in several parts. I mean, first I will give an introduction to random tensors, and I will talk a bit about the motivations behind looking at such models. And then I will explain how random tensors address a particular question, namely how random tensors provide a theory of discrete spaces. And in the introduction, I would supposedly I'm convinced you that one should be interested in looking at something like this, and then I'll explain how this comes about in random tensors. And then I will talk about some more recent developments concerning free cumulants and the large N limit, in these models. And this last part overlaps a bit with a presentation which took part in the seminar series maybe 1 month ago by Luca Lioni. So you can always, go back and also look at a bit more details there. I mean, my presentation is more of an overview. It's supposed to be a bit less, precise. So if you want to go see the true, nature of our results, you can maybe go in there. Okay, then I'll explain with some conclusions. Okay, so the story of random tensors, starts with random matrices. So random matrices have been introduced a long time ago by Wishart in 1928, so almost 100 years ago. And then they were first used in physics by Wigner in 55 to discuss the spectra of heavy nuclei. And since then, random matrices found applications in a plethora of fields, from the theory of strong interactions to random surfaces. They describe birds perched on wires or parked cars, and also they are relevant for pre-probability theory. And what is special about random matrices is that they come automatically endowed with a parameter. So if you talk about a random n by n matrix, the size of the matrix n is a parameter. So you can always convert it in a small parameter by looking at 1 over n. If n is large, then 1 over n would be small. And when one takes a limit in any kind of theory, the theory simplifies. I mean, hopefully enough, or maybe not, but at least it simplifies. And the attempt is to maybe start the large n limit first, into infinity, large matrices, and then look at corrections in 1 over n. And it turns out that in a plethora of problems, this strategy works, and one can understand these, problems by first looking at infinitely large matrices and then taking, corrections with respect to this limit. So, seeing the many applications of random matrices, one question one might have, it's okay. How about tensors? Can something be done, slightly similar to random matrices in the case of tensors? So matrices have, they are tables of numbers, and the tensors would be like hypercubes of numbers. So can one try to understand random tensors a bit in the same spirit like random matrices? And this is a story that has been going on for some time. So the first generalization of random matrices to tensors, they date back to the early 90s. And they arose in physics in the context of studies of random geometry. And since then, we have a number of results which date back maybe 15, 20 years. We know today that random tensors do exhibit an 1 over n expansion, a bit reminiscent of the one of random matrices. However, they exhibit a new large N limit, which is different from the limit of random matrices. It's an interesting new large N limit people can study. And this has been exploited to study models of large N field theory. So, these are, field theoretical models in which the field itself is a tensor. So it has several indices. And then in the large N limit, things happen. And such studies are relevant for the study of spin glasses or maybe for tensor principal component analysis and so on. So these are, if you want, what I would call more classical results. Recently, over the past maybe 3 years, there have been an increased effort to try to generalize the notion of free probability, notions of free probability to tensors. So we have a good theory of free probability, which describes random operators, which kind of is the larger limit of random matrices. And one can argue, one can wonder, can one find something similar for tensors? Can one describe an ab initio theory of random infinite tensors? So the strategy would be, the strategy pursued, by some people in this direction was to essentially try to first look at finite tensors n and then take the larger limit. identify, understand this larger limit, identify the intrinsic defining properties of object in this limit, and supposedly this should lead in the end at a self-contained formulation of the limit theory without first going to the large n, to this finite n step, So one hopes to identify the correct algebraic structures which describe this larger limit and then build objects which, essentially respect these things, So this would be like an infinite random tensors would be an object which respects a certain number of properties. And you can find many more details about this category of results in Luca Leoni's talk, which took part on the 3rd of October. So you should find it in the, videos of past talks in this seminar series. Okay, so what I will be telling you about today, well, today I will give a bit of an overview of two classes of results. So first, what would by now be called classical results in this theory of random tensors. And namely, I will want to make a point that contrary to random matrices, random tensors are much richer because one essentially has to deal with many more invariants. So in the theory of random matrices, one is interested in invariant objects, in invariant observables, and for tensors, again, in invariant objects. However, the number of invariants is much larger for tensors, so the theories are much richer. Also, I will briefly mention the connection between random tensors and random geometries. So I will explain a bit how these models can generate random geometries. And I will discuss a bit the 1 over n expansion and larger limit, but not in great detail. A second class of results I want to discuss briefly are more recent results, which are a bit related to this problem of adapting, finding a correct generalization of free probability to random tensors. And I will focus on two results. First, I will discuss moment cumulus relations, which appear in the large and asymptotic regime of random tensors, which are a bit similar to the one of random matrices. And then I will mention a slightly surprising fact, namely that at large n the factorizations do not hold, the expectations do not factor for random tensors. This is contrary to random matrices, and I will explain a bit at that moment why this is a relevant thing and why this is a bit surprising. Okay, so that's the plan for today. However, before starting, let's try to give ourselves a bit of motivation. So why would one be interested in random tensors? Now, there are many reasons to be interested in them. One of them is the theory of random discrete spaces. So the question is, why would one care about random discrete spaces to begin with? And the reason is that random discrete spaces, they arise naturally if one thinks a bit about the following problem. So in physics today, we have essentially two theories which work very well in the realm of applicability. So one of them is quantum field theory, and that is something which works very well at small scales, and the essence of quantum field theory is that, the theory is described by a path integral. So one needs to essentially understand the probability measure with a weight which is exponential minus some action. And this action, contains maybe the standard model action with, leptons, quarks, gluons, bosons, and so on and so forth, And the main lesson of quantum field theory is like, well, in order to understand correlations, which are the predictions of the theory, one needs to sum over random configuration of dynamical fields. So in quantum field theory, the main lesson is that, at some point we need to sum over random configuration of fields. Now, at the other end of the spectrum, at very large scale, we have the theory of general relativity. And this essentially tells us that at a very large scale, matter and geometry, they are connected via an action, it is a geometrical action, this Einstein-Hilbert action, which has this part, this is the Ricci curvature of the space-time and maybe a volume term, to see the cosmological constant. And then this is coupled to a matter, Lagrangian, the matter in the, for instance, cosmology context, it contains visible matter, dark energy, and so on and so forth. So starting from this classical action, so this is not quantum, it's just classical, one can derive, for instance, equations of motion. And one obtains these, interesting equations which tell you that on the one hand, something purely geometrical on the left-hand side of this equation, this is a tensor, which is the Ricci tensor, the Ricci scalar, and the metric. And this is something which needs to be equal to the stress energy tensor of the matter fields. So this tells you that essentially, the matter fields will render the geometry dynamical. So in general relativity, geometry is dynamic. So we have two kind of, lessons which we learn from these two theories. At small scale, one is to sum over random configuration of dynamical fields, and the geometry is dynamic. Now, in principle, because these two things are very separated, so one applies at very small scales and one at very large scales, one could live with this, you say, okay, I have a good theory at small scale, a good theory at large scale, and that's life, However, one needs to be aware that in fact there is a regime in which these two theories need to be at the same time, applicable. And this comes about as follows. So if one considers a photon of frequency nu, so we know that quantum effects, quantum field theoretical effects, quantum mechanical effects will be observed when one will look at this photon with a apparatus which is able to essentially detect objects of the size of the wavelength of this photon. So this is something like the speed of light divided by the frequency. However, any photon has an energy which is proportional to the frequency, and we know that any energy has a mass equivalent. So a photon has a very tiny mass equivalent. And in general relativity, we know that if you try to focus a mass in a point, at some point you will generate a black hole. A very tiny black hole with a very tiny horizon. But if you really try to squeeze all the mass in one point, this black hole will have a non-zero size, and this size is the Schwarzschild radius associated to the mass of the to try to focus in a point. So a photon also has an associated Schwarzschild radius. So you have these two scales, and at this scale you expect to see quantum field theoretical effects at the Compton wavelength scale, whereas at the Schwarzschild radius you expect to see general relativity effects. So, however, there is a scale which is essentially the average of these two, the geometric average of these two. So this is, you can compute this scale. It's a number. It's 10 to the minus 35 meters, and you expect that this length scale, which is called the Planck length, but both things play, a bit of they're a bit on an equal footing. So at this length scale, one should try to make sense of something which is a sum over, random configurations of geometries, so geometries, metrics, and so on and so forth, and then also matter. And then an exponential should be a geometrical action, something which is geometry, something which is the curvature of your, manifold or so on. So, and I mean, of course, the goal to make sense of this is the goal of the theory of what one would, calls quantum gravity. Of course, this theory doesn't exist, because unfortunately, this Planck length is not really accessible experimentally, so it's very difficult to actually make, experiments. So then one tries to build theories which could put together, some kind of geometrical object with a sum of a random geometry. So some geometrical action with a sum of a random geometry. Now, this is not easy. This is a complicated problem. And among the approaches in trying to make sense of such a, sum over random geometries, but one idea is to discretize. So, one approach to try to make sense of this path integral for random, geometries and metrics would say to replace it by a sum over random discretizations. So one essentially takes building blocks, which would be what would call maybe space-time quanta, so it should be small bits of geometry, and one starts to put these things randomly together and obtains a sum of a random discretization. Now, as a function of the details of the theory, you get various weights for these, random geometries. You add them up together, and you expect that, when you have enough of these little quanta together, you'll get an ensemble behavior. So instead of having individual guys, you'll have like the ensemble will acquire some effective behavior, and you would hope that maybe in this effective, ensemble behavior, one can then try to identify various features, of this theory of quantum gravity. So the main message of this is that it is interesting to build models of random spaces. So one application of these models of random spaces is in this context of trying to quantize gravity. Okay. Now, one of the messages today will be that tensors can do that. Random tensors can provide the theory of random discrete spaces. So this is one of the reasons to be interested in such models. Okay. So now I will go maybe to the more detailed presentations of what random tensors are. So it's a good moment to maybe stop and ask if there are any questions about, the big motivation, why we are interested in such models. Okay, so I will assume that there are no questions and people are motivated. So let's start. Okay. So first of all, before discussing the connection between random tensors and discrete spaces and other features of random tensors, let's see first what random tensors are. So again, the story starts with matrices. So what are random matrices? So a random matrix is a table of n square numbers. And so that's a matrix, and what makes it random is that I look at the probability distribution over this table of numbers, and what makes that these numbers form a matrix is that I look at probability distributions with certain invariance property. So for instance, one considers the probability distributions for Hermitian matrices. So typically this would be something like this. If there is a Lebesgue measure here on the matrix entries and then some weight, some probability density, which I take it to be invariant under, for instance, conjugation of the Hermitian matrix here, conjugation under the unitary group. So one way to build an invariant is to take a trace of an arbitrary function of h, and well, this probability density here, then it's invariant under unitary transformations, and one can wonder, okay, I want to understand this probability measure, with this invariant probability distribution. One can also consider matrices which are not necessarily Hermitian. So this would be an arbitrary matrix M. Then the natural invariance is to have two different conjugations, one on the left index and one on the right index. And when I do this, it turns out that the invariant objects are more, traces of products of M dagger times M, because you see, if I multiply M dagger with M, then U dagger comes in contact with U, and if they are unitary, they drop. And then I take a big trace and I kill the last, unitary on the outside. So such measure, it's an invariant measure for a matrix, arbitrary matrix, unnecessarily Hermitian. Okay, and the theory of random matrices essentially is concerned with studying these probability measures. What can I say about these probability measures? Now, I said that random matrices have to do with birds, so we can ask where are the birds in this story, because we talked about matrices. So the birds come as follows, come about as follows. So consider the simplest possible probability distribution for a random matrix. That's a Gaussian distribution. So that means that I take here as function just the h squared divided by 2, so it's just a Gaussian thing. And well, I mean, then I have a probability measure which is invariant under the unitary group. And one can actually integrate over this unitary group. So then, once I integrate over this unitary group, I get a remainder, a probability distribution over the eigenvalues of the matrix. And, the probability density has two bits. So one of them comes from the Gaussian part. And this is this exponential minus n half times the sum of the squares of the eigenvalues. And this is a confining potential. This tells you that the eigenvalues really want to be set to 0, all of them, because the a very big factor in the size of the matrix in front, they want to be 0. However, when I integrate over the unitary group, I get a Jacobian, or if you want the Faddeev-Popov determinant. And this, guys, it has this form, is this van der Monde determinant here. And this van der Monde determinant, well, has the property that when two eigenvalues are equal, this is exactly 0. So you see that we have here two competing effects. On the other hand, the eigenvalues, the confining potential wants to put them in all at the origin. On the other hand, they repulse a bit, so they can't really be at the origin. So then they distribute themselves, over some interval, with some spacing between them. And it turns out that this kind of effect actually, it's this kind of phenomenon is very common in nature. For instance, if you have birds perched on wires, here, the wires are finite, so this gives us a confining potential. And on the other hand, the birds, they are fermionic, so they can't really occupy the same space. They can't, be on top of each other. Moreover, they like to move around a bit, so there's a slight repulsion between birds, when they sit on the wires. So when you look at the gap distribution between birds on the wires, you get the statistics, and this statistics turns out to be very well reproduced by the distribution of spacing between eigenvalues of a Hermitian matrix. Okay, so this is how random matrices apply to birds. I mean, the big question in this field of research for me is, why does this distribution fit the Hermitian matrices? Because if I take slightly different models, if I take non-Hermitian matrices, then I get slightly different distribution of spacing between eigenvalues, and the birds, they really seem to fit very well the one of the Hermitian matrices. So it's unclear to me why. But this is the good spacing distribution for birds perched on wires. Okay. So now these are random matrices. What are random tensors? Well, the basic building block of random tensors are tensors, So as I said, random matrices are tables of n square numbers. A tensor will be a hypercube of n to the power d numbers. And for the interest of this talk, I will put always d on the slides, but I will mainly talk about the tensors with 3 indices. But this applies with tensor with 4 indices, 5 indices, and so on and so forth, So a complex tensor, it's a pair of objects, with indices a1, a2, a3, t and t bar. And the number of values of an index is n. So this object has n to the power cube indices for 3 indices, well, that's a tensor. So what is a random tensor? Well, it's a probability measure for these complex numbers, which such that the expectations are invariant under an appropriate transformation. And in order for these objects to be tensors, the appropriate transformation is what's called a local unitary transformation, which goes as follows. Namely, I take every index of the tensor and I turn it to its own unitary. So I have a unitary u1 acting on the first index, a unitary u2 acting on the second index, and so on, and the distinct unitary acting on the last index. And when I have this transformation law for the tensor T, then the complex conjugate T bar will just pick bars all over the place. So I have this associated transformation law. And then in the random tensor, it's a probability measure such that the expectations are invariant under this transformation. So they have this property for any functions of T and T bar. The expectation of F is the expectation of the function for the rotated tensor. So this is an invariant probability distribution for such objects. So you see, I've gave you here the transformation law, and I mentioned the word invariant several times. So a first task would be to build invariants associated to this transformation. So how does an invariant object look, built out of tensor and T and T bar, under this transformation? And well, the story goes as follows. If I had to deal with matrices, it's very easy to build an invariant. Essentially, if I look at polynomial invariants, there is a unique polynomial invariant I can write at a given degree. Its name is the trace of m dagger times m to some power. And that is, essentially the only thing I can write. Now, for tensors, the situation is much more complicated. So as I was mentioning before, these models are richer. They have a zoology of invariants. And the reason is the following. So suppose that I take this transformation law for the tensor T and T bar, and I try to just generalize this notion of a trace, for tensors. So what I need to do in order to build the invariant is just to take, polynomials in the tensor entries and then to contract indices. And to make sure that I have an invariant, I need to contract indices respecting the position. So any kind of, monomial with contractions like this, well, it is such that when I turn this first index with an unitary U, and I turn the corresponding index on the tensor T bar with the U bar, well, then U and U bar come into contact and drop. So this is an invariant object. But you see, there are many ways to build monomials, with contractions like this, with respect to the position of the index. And it turns out that such monomials can be represented by colored graphs. And the representation goes as follows. So first, let's take an example. So I take this example here. So this is an invariant object. It has 3 tensor T and 3 tensor T bar, and it has contractions between the indices. And if you notice here, I chose the contraction such that I respect the position. So the first, the first contraction here contracts an index A1 with an index P1, meaning that I contract the index A1 on this tensor T with an index P1 on this tensor T bar. And then the second contraction, it contracts A2 with Q2. So it's the A2 here with the Q2 on this other tensor, and so on and so forth. So all these contractions are such that they contract an index on the tensor T with an index on the tensor T bar respecting the position. Now, for this contraction pattern, I will draw a graph, an associated graph. And the construction goes as follows. So first, I draw a vertex for each tensor. And because I have 3 tensor T and 3 tensors T bar, I will draw a white vertex for the tensors T. And I'll say this one represents this T A1, A2, A3. And the second one here is the T B1, B2, B3. And this is T C1, C2, C3. And then a black vertex for the T bars. So I get, all in all, 6 vertices. Now, for every contraction, for instance, this contraction here, it contracts to indices. So I will connect the vertices corresponding to the 2 tensors on which these 2 indices are by an edge. So, this edge here represents a contraction of the index A1 with the index P1. So when I see two tensors, 2 vertices connected by an edge, it means that I have a contraction, in between the 2 indices on these tensors. Now, because my contractions respect the position, I can promote this position to a color. And I can say this is an edge of color 1, because it represents the identification of the first index here, A1, with the first index here, P1. And this is the one, the color is the first index which is identified. And then I can do this for the second index, for instance, the delta A to Q2 here. It identifies the index A2 on this tensor is the index Q2, which belongs to this other tensor here. So that's an edge of color 2. And then for the third index A3, R3, so this connects the index A3 here with the index R3 here. So you see that every contraction can be represented as an edge which bears a color. So if I take all the bunch of delta functions here, I get this graph. So this represents the identification of these indices in this invariant. And you see that the graph obeys certain rules. So it has 2 classes of vertices, black and white, representing tensors T and T bar. They are connected by edges such that every edge has a color 1, 2, or 3, because the index has a tensor has a first index, a second index, or a third index. And such that for every vertex, every color is incident exactly once, because the tensor has only 1 index in the first position and only 1 index in the second position, or 1 index in the third position. So these objects are called regular edge D-color graphs, or 3-color graphs if you want, So they are, combinatorial object which encodes this invariant. Now, it turns out that one nice way to index these invariants is actually to index them through permutations. So essentially, I can label my vertices, and I will label the white vertices 1, 2, 3, and the black vertices 1 bar, 2 bar, and 3 bar. And to every colored graph, I can encode every colored graph in a triple of permutations. So I will say that, a permutation 1, 3, 2 over, for this is one possible permutation over 3, over the labels 1, 2, 3. Well, I will associate to this the edges 1 going to 3 bar, 3 going to 2 bar, and 2 going to 1 bar. So this permutation encodes these red edges oriented from the white to the black vertex. So I have a permutation for the white vertices. I have a second permutation for the blue vertices. So that would be 1 to 1 bar, 2 to 2 bar, and 3 to 3 bar. So this is the permutation 1 to 3. And for the green vertices, I have 1 to 2 bar, 2 to 3 bar, and 3 to 1 bar, which is this permutation here. So for any triple of 3 permutations, I get a possible graph. Now you see that here I labeled my white vertices 1, 2, 3, and the black vertices 1 bar, 2 bar, 3 bar. So if I permute the white labels between them, I did not change the graph. If I permute the black labels between them, I did not change the graph. So this means that overall, a rough estimate of how many different graphs I have at an order n, I mean with 2 n vertices, is n factorial to the power, the number of indices, because I have one permutation per index, to the minus 2, because 2, I lose 2 permutations for labeling the vertex. But what does this mean? If my tensors have 3 indices, I get roughly n factorial invariants. If my tensors have 4 indices, I have roughly n factorial square invariants, and so on. Whereas for matrices, I deal with only with objects with 2 indices. So what I get here is n factorial to the power 0, which is 1. So I get only 1 invariant. So you see that I have a big change, from essentially 1 invariant per order to something which is super exponential. I have n factorial invariants at a given order. So that is plenty of invariants. So these tensors, they generate a lot of invariants. And well, I mean, graphs are plenty of graphs, some of them are complicated, some of them are simple. A particular simple family of graphs, but it's infinite, and there are at any order an infinity of them, are the so-called Meloni graphs. And they are the simplest category you could think of, and they look as follows. So, a particular infinite family of invariants can be obtained by starting with the simplest possible invariant. So this contains a tensor T and a tensor T bar, and all the indices are contracting between the two. So it represents this graph here with 3 colors. And that's one invariant. And then I can build from this another invariant by essentially taking 2 edges connected, 2 vertices connected by 2 edges and inserting it arbitrarily on any edge here. So for instance, this would be a second invariant in this family of invariants, but I can insert this decoration on the green edge, respecting the colors, or I insert it on the blue edge, and then I can start again and insert it further. So this makes that I generate an infinite family of possible invariants, relatively simple by these iterative insertions. And for obvious reasons, because they look like melons, they are called melons. So a slightly less trivial example is, for instance, this graph here. It's obtained by making 3 successive insertions, and it has, for instance, I can start from this guy here, and insert once again on the, so this is also inserting on the edge. Okay, I can insert twice, for instance, small invariants on the blue edge here, and I get the graph here, yeah. However, there are plenty such melonic invariants. For instance, all these graphs are also melonic. They could be disconnected. These are also melonic. The small graphs here are also melonic, on the right and so on. So you see that there is a plethora of such invariants, melonic invariants. So already in this simple family, it's clear that I can draw many more graphs than this, but already this simple family, it's an infinite family of invariants one can consider, Okay. Now you could say, okay, you showed us plenty of invariants, but do we actually need all of them? I mean, there are this kind of factorially many invariants, but are they independent? And the answer is, in fact, they are for large enough tensors. So if I take tensors whose indices, the size of the indices is, large enough, so this size of the indices needs to exceed essentially the number of invariants, then the family of invariants, it forms a basis. The family of these invariants indexed by permutations forms a basis in the space of homogeneous invariant polynomials of degree n in T and T bar. Yeah. So if I want to take an arbitrary polynomial invariant of a degree, n in T and T bar, for large enough tensors, I need all of these invariants in order to, to express it as a linear combination. Yeah, so these guys are really, all of them are independent, for large enough tensors. A bit like the traces of the powers of the matrix are independent for large enough matrices, So if I want to have that the first traces up to power n are independent, then I need to take matrices which are larger than n times n. Yeah? So a bit the same phenomenon happens here for large enough, size of the tensors. These all invariants are, linearly independent because they form a basis. So that's the first message of my talk today. Tensors, random tensors have a zoology of invariants. They are, factorially many, much more than you have for matrices, which essentially have one invariant per order. Okay. So because this was the first message, are there any questions so far? Okay. If there are not any questions, then I'll continue to my second message of the day. And the second message consists, in the connection between these models and random geometries. So what is random tensors? What do these random tensors have to do with discretized, random discretized spaces? So the connection, can be, is simplest to be understood doing the following. One considers probability distribution for tensors, and this will be an invariant. So I said that I want to take here a probability density that is invariant. So the natural thing to take, it's, maybe some action, exponential of some action, some scaling factor. It's a bit conventional, the scaling factor here, times an invariant action. And for the invariant action, well, I will put here my simplest invariant. So this represents the simplest graph. I showed this Meloni graph. It has a T and a T bar connected, by edges, the edges, parallel edges. So this is the only quadratic invariant one can write, for the, a tensor in its complex conjugate. But then I will add a perturbation to this Gaussian measure. So I will add here a sum over essentially some graphs, some of these connected graphs with d colors, So I will treat this as a measure, which is a Gaussian measure plus a perturbation. Now, the kind of interesting objects I try to compute, would be something like expectations of observables. So the right observables are my invariants. The invariant observables are these traces, And I could be interested, for instance, in computing the expectation of a product of such traces. So that would be an interesting object to compute. Or maybe the partition function z or its logarithm, the free energy of such a probability measure. Okay. So how does one go about computing these expectations or this free energy? Well, I mean, in physics, one essentially has a kind of a powerful machine at his disposal, the so-called Feynman expansion. So this goes as follows. If I want to estimate, the integral of such a probability measure, well, the strategy, is the following. I will treat T sigma as perturbation, so I will Taylor expanding this coupling constant. So I Taylor expanding coupling constants. Each coupling constant multiplies the trace invariant. So each coupling constant, it's comes equipped with one of these drawings having 3 colors, corresponding to its invariants. But then I need to compute the Gaussian integral of a product of such invariants. Yeah? So I need to compute the Gaussian integral where the insertions are such invariants. And these Gaussian integrals, they are computed in a standard manner via Wick theorem, which tells me that essentially I get sums of pairings between tensors. These are the Wick pairings where you have propagators in the field theoretical language. So on top of my invariants, which had 3 colors, I add an additional color, which comes from this Wick pairing, So this partition function, or its logarithm, will write as a sum over graphs having an additional color. So they have 3 colors coming from the invariants, the red, the blue, green, colors come from the invariants. And then they have these additional dashed edges, which have a new color. One could call it the color 0 if you want, which come from the Wick contractions between these tensors T and T bar. So bottom of line, combinatorially, this partition function is a sum over graphs having 4 colors. If I start with tensors with 3 indices. And I mean, for each of these graphs, I have a certain amplitude which one can compute. But before computing amplitudes, let's just look carefully at what this is. This is a sum over graphs with d plus 1 colors. Well, the point is that each of these graphs, for instance, with 4 colors, if I have tensors with 3 indices, this graph will have 4 colors. In fact, it is embedded in a 3-dimensional space. So each of these graphs represents a 3-dimensional triangulation. So this partition function is a sum over 3-dimensional triangulation. So how does one build this triangulation? Well, there's a canonical construction, which is relatively easy to understand, and it goes as follows. So ideally with graphs which have black and white vertices.
Razvan,
Yes,
can I ask a question about the previous slide? Here I somehow got a bit lost. So this S is this action which has as this first term, which something that looks like a Gaussian, right? This
exactly.
T, and then, but I thought if I have only two matrices, two tensors, that's the only invariant function. What is the second term then?
That is
This
the
connect.
only, this is the only quadratic invariant I can write, T times T bar.
Uh-huh.
But if you see, if I have, I
Ah,
can write, for instance, invariants of order 6, this would be an invariant at order 6. You know, this one would be an invariant at order 6.
gotcha.
So I
Thank
can
you.
put a perturbation with a T cube, T bar cube in it, which has this particular contraction pattern. And I can put as interaction, I can put also quartic invariants or invariants of order 8 and so on and so forth. So this contraction is the unique quadratic contraction I can have. But these guys, they have more than two T and a T bar. So this is why I drew them here, for instance, as this particular contraction pattern of 6 tensors. This would be one possible candidate to put here. And this
Yeah.
different contraction pattern of 6 tensors, it's another possible candidate to put here in this interaction.
Okay. Thank you. Thanks.
So now when I compute this Gaussian integral, I add on top of these contraction patterns which come from the invariants here, I need to add an additional contraction coming from the Gaussian pairings, from the Wick theorem. Okay. So are there any other questions? No, if there are no other questions, then I continue. Okay, so I promised you that I will associate a triangulation to such a drawing with 4 colors. So this goes as follows. You know, my vertices here are 4 valent vertices. So around each of these 4 valent vertices, I will draw a tetrahedron. And because the edges are colored, well, there are 4 edges emanating from this vertex. So each edge, will pierce one of the triangles which bound this tetrahedron. So the green edge, for instance, pierces this triangle, and the red edge, the one behind, and so on. Now, because my edges are colored, well, you see, this edge goes, pierces this triangle. So in a tetrahedron, there is a unique vertex which is opposite this triangle, which is the vertex on the other side. So I can take the color of this edge, green, let's say, and send it on the vertex here. So this vertex here is colored green. And I can play this game for all the vertices of this tetrahedron. So the red edge there, I send the color red on this vertex. For the blue edge here, I send the color blue on the vertex behind there. And for the black one, I send the color black on this vertex. Now this corresponds, for every edge, I can draw a tetrahedron around it. And now for every vertex, I glue tetrahedra along triangles, because, these edges, they go through triangles. So for every edge in the graph, I will glue these two tetrahedra together along a triangle. Now, because I have these colorings of the vertices, well, I will take here the unique gluing, which respects the colors. So my vertex, which has been colored red on the tetrahedron on the left, is glued on the vertex which is colored red on the tetrahedron on the right. And the same for the blue vertex and the same for the black vertex. So like this, I can, starting from these colors, I can build coherently a unique triangulation associated to the graph. And in fact, if you want to be very rigorous, one can prove that the color graph by itself is a cellular complex, and the triangulation you build here is actually the Poincare dual of that cellular complex. So this is how you build it by hand, but there is something behind which tells you that this is the unique, it is the Poincare dual of the graph complex. This triangulation I have built here. Okay, so this tells me that my graphs here, they are graphs with gluing of three-dimensional tetrahedra. So they are actually discretized spaces obtained by gluing tetrahedra together. Now, if I look at for instance, expectation of a product of trace invariants, each trace invariant has one less color. So each trace invariant, it's a graph like this with only 3 colors. So if a graph with 4 colors corresponds to a 2-dimensional triangulation, a graph with only 3, so this invariance will correspond to a 2-dimensional triangulation. So what I compute here, actually, it's the correlation between boundary triangulations, 2-dimensional boundary triangulations. Each of these invariants here, it's a boundary triangulation. It can represent, for instance, a spherical boundary component, or a torus boundary component, or a donut with several holes, whatever, And, the expectation of these boundaries, well, it's a sum over all possible ways to build in bulk triangulations, 3-dimensional triangulations, which connect coherently these boundaries. Yeah? So this, this expectation automatically sums over all possible bulks, which connect between the boundaries. So this is a cobordism, if you want. It's something which goes from a boundary to another boundary and fills in the bulk between the two. Now this is where the discrete triangulations come into play in this business. In these bulk triangulations which are summed between boundaries. Now each of these triangulations comes with a particular weight. One can compute this weight and so on and so forth. But before talking about the weight, one should see that automatically this probability measure generates sums over triangulation with certain. Okay. So is this clear? I mean, especially, I hope that you understood the answer to this question about the invariants. So these invariants, they are crucial. They are the, non-quadratic invariants. They are, power 4 in the tensor or 6 and 8 and so on and so forth, and they give you the pieces here which are then glued, to form the big triangulation, the big three-dimensional triangulation. Okay. Now, bottom of line, the situation goes as follows. One can compare the, random matrices and random tensors. And the situation is that for random matrices, if I take an arbitrary invariant action here, well, the partition function, is written like this. And if I can compute the free energy, it is the sum over triangulation with a certain weight. And this weight C is the size of the matrix N. And something very similar happens for tensors. If I have the partition function is exponential minus, some action, which is, quadratic part plus perturbation. Well, if I look at the partition function associated to this is also a sum over triangulations. And the triangulations also come with a certain weight. I can compute this weight by computing the Gaussian integral. And it turns out that this weight is very interesting because it's a series in N. So it starts at order N to the power 0. And then it has corrections in 1 over N. In the case of matrices, these corrections are indexed by the genus of the surface. So this partition function is sum over surfaces, and we have the planar surfaces that are leading order, and then we have the genus 1 surfaces, they are corrections, and genus 2 surfaces are corrections, and so on and so forth. Now, in the case of tensors, you have something very similar. This free energy is also a sum over triangulations, but this time they are three-dimensional triangulations. So they are spaces, three triangulations of spaces, and they come endowed with a factor of N. So I have a leading order class of triangulations, which are triangulations where this omega is 0. And then there are corrections, triangulations of this omega is 1, and so on and so forth. So for matrices, we have this series turns out to be indexed by the genus of the surface. For tensors, it is indexed by a non-negative integer, which we call the degree, and it's not the genus, this is something which, exists in higher dimensions, for higher dimensional triangulations. Now, moreover, it turns out that if we restrict to the leading order, then in the case of matrices, this projects on triangulations of genus 0, which are the simplest possible triangulations. They are spherical triangulations or spherical topology. And in the case of tensors, something similar happens. At leading order, so when this degree is 0, I only get spherical triangulations. So the leading order behavior is dominated by spherical topologies. However, one should make a small comment, whereas in the case of matrices, I get all the triangulations of spherical topology at the leading order. So this guy captures all the spherical triangulations. This is not true for tensors. So in this melonic order, it turns out that in this order only the melonic triangulations contribute, which correspond to melonic graphs, the ones which you've seen by these iterative insertions. Well, all of them have spherical topology, but not everything which has spherical topology has such a triangulation. So there are some spherical topologies which are triangulated a bit in a different manner, which are not captured by this leading order. So, while this is spherical, it is not all the spherical triangulations. So it's a bit different between random tensors and random matrices. Okay. So with this, I kind of finished. If you want to review the more classical results on random tensors, so this is a good moment to ask questions if you have questions about this first part of the talk. Okay. If you don't, then I will go to discuss a bit some more recent results. So now I kind of turn a bit the page. So far I talked about the geometrical aspects behind random tensors, the number of invariants in random tensors, and so on. So now I will switch a bit and try to build a theory of random infinite tensors. Now the way is very long to get there, so we will not get there today. However, there are some intermediate results we have on our way to get there. And namely, one of the things we've been able to do, we managed to define a good notion of recumulants. And I hope I managed to convince you why this is a good notion to look at, and then to try to understand their large and okay. However, before talking about cumulants, one needs to go back a bit and understand what cumulants are. And the story goes as follows. So suppose that we take some random variables, and I look at the joint expectation of x1 to xn. So you know that an expectation of a product of random variables writes as a sum over product of connected expectation. So for any expectation, I can say that this expectation, it's the sum over partitions of these guys in parts, and then I put a connected expectation for each of the parts. Now this is a linear relation between connected expectations and connected expectations. Sometimes these are actually called also cumulants. And because it's a linear relation, this relation can be inverted. So the fact that this can be inverted comes from the fact that these partitions, they form a lattice. So one can use Möbius inversion in the lattice of partitions. Then one can write the connected expectations as linear combinations of expectations with some coefficients here. And these coefficients, they depend on the lattice, and they are called the Möbius function of the lattice. So for the particular case of the lattice of partitions, they have this explicit form here. It's not maybe very relevant. Okay, now these relations between expectations and connected expectations can be written in a very symmetric form. If I take the multiplicative extensions of expectations and connected expectations, and it just takes this very simple form. The expectations write as a sum over all the partitions in the lattice, of partitions between the one set partition and the partition in n sets with one element of k with coefficients 1. And this is inverted in saying that the connected expectation associated to the partition in only one set is this sum over partitions in the same lattice interval of the expectations times these Möbius functions. So such relations are called moments cumular relations in any lattice. So whenever you have some e's and some k's which are related by such a relation, well, the e's will be called moments, k will be called cumulants, and this will be the associated lattice for this thing. And the main message, which I would want to convey to you is that there is a good notion of large and asymptotic moments, so something which plays the role of this E here on this right-hand side of this equation, and the asymptotic cumulants, so something which plays the role of this K, the connected expectation on the right-hand side of this equation, and the good lattice, to replace the lattice here, which is the lattice, in this case, it's lattice of partition, but there's another lattice one can use, such that in the case of random tensors, if I take the Largen limits, I have a Largen asymptotic expression of this form. My Largen asymptotic moments write as a sum over, in a certain lattice of Largen, asymptotic cumulants. Okay. Now, why is this relevant? Because you say, okay, this looks complicated, so why do we care about it? So the reason to care about this is that, in fact, once I establish this Largen asymptotic moments, asymptotic cumulants relation, I can just say, okay, this is a good starting point for an ab initio study of the limit object. So I will define a limit object as an object which respects directly this asymptotic relation between asymptotic moments and asymptotic cumulants, and I can try to look at its universality properties. And this strategy actually works in the case of matrices. So one starts from finite size matrices, one gets to these asymptotic relations, and one then defines, if you want, like free random variables as the variables which respect this asymptotic moment cumulants relations. And then one can develop an entire theory of free probability based on it, which turns out to be the theory of random operators in Hilbert spaces, essentially, So without any need to talk about matrices again and so on and so forth, just starting from this asymptotic moments cumulants relation. So it is important to identify appropriate asymptotic moments cumulants relations. Okay. So, okay, how does this work? So first, let's look a bit about matrices. Well, there is a slight subtlety. So the subtlety is that, if one talks about moments cumulants relations in matrices, one does not talk about the naive connected expectation. And this comes about as follows. So consider the simplest possible example of a matrix. This is a Gaussian matrix, distributed here with a Gaussian measure. And well, because this is Gaussian, I know how to compute the expectation of any product of matrix entries. And this is a sum over just the two, sum of products of this 2-point connected expectation, because this is the only non-trivial connected expectation. However, these are not these connected expectations between matrix elements are not the connected expectations one is interested in usually. So in the case of random matrices, one is interested in other connected expectations, which are defined more in the following manner. The connected expectations between two invariants, trace of MMDAG times trace of MMDAG, where is the expectation of the product minus the product of the expectation of the invariants. So this object is connected in the sense that I want to make sure that the m's from the first invariant are connected to the m's in the second invariant. So this is some kind of a connected expectation. Is this also called the classical cumulant between these two invariants, which is not exactly the connected expectation between matrix elements. It's something different. Yeah. So it turns out that one can define properly what one means by this classical cumulant, this connected expectation between invariants. Well, is defined by a moment cumulant relations in an appropriate lattice, in fact. And the lattice is relatively simple. So essentially, these classical cumulants are defined exactly as the connected moments, but it's just that I restrict that my partitions need to respect the connected components of my observables. So you see that here I have these invariant observables, and instead of taking all the partitions in the sum here over the n elements, between the matrix elements, I require that this partition respect the connected components of my invariants. So essentially here I partition my vertices, but just between invariants. So with this definition, the connected moment, can be written as this linear combination of expectations. And now this is what is the definition of the classical cumulant. And this can be inverted because this is essentially the same lattice as before with the Möbius function. And this allows me to write the expectations in terms of the classical cumulants. And maybe the most, if you want, familiar expression here is this one. This allows me to write that the expectation of the product of three invariants, trace of sigma 1, trace of sigma 2, trace of sigma 3, it's first the classical cumulant between sigma 1, sigma 2, sigma 3, all of them connected together. So all the three invariants are connected together, plus three terms which connect, this one connects sigma 1 of sigma 2 and sigma 3, it's apart, and it's friends. And then it's a last one, which is just the connected, the cumulant sigma 1, cumulant sigma 2, cumulant sigma 3. So you see that this expression here tells us that this expectation essentially is divided in either the term when everybody, all the invariants are connected together. This is the first term. This is the second term where two invariants are connected together and the third invariants apart, and then a third term when all the invariants are separate. Okay. So this is the definition of classical cumulants. They are better adapted to matrix, random matrices, and one has moments cumulants relations. They're given here. They're in the appropriate lattice. It's still a lattice of partition, but with this constraint. Now it turns out that this can be actually stated in terms of partitions among the connected components of my my invariants. Okay. Now, in the case of matrices, however, one has a second notion of cumulants, which is important, and these are the so-called free cumulants. So the free cumulants are defined as follows. One can take the generating function of connected moments. So this is up to some scaling in front. The expectation of the exponential of j times t, j bar, t bar, and jt, where j and j bar are sources for the tensors t and t bar. And this is an invariant object because we said that you take a probability measure, which is an invariant probability measure. So because this is an invariant, it can be expanded on the basis of invariants, which, as we said, are these trace invariants, these drawings, So this is a sum over these trace invariants for the sources j, j bar, times some coefficients. And these coefficients, they are called free cumulants. Now, this can be computed, it's a bit of a lengthy computation. And they have a specific formula in terms of the classical cumulants. So starting from the classical cumulants, one can build free cumulants essentially via a linear combination. Now, this linear combination is a bit ugly. I don't expect you to understand, the details of this formula. The point I want to make is that, one can define these free cumulants for matrices, and one has a straightforward generalization of these free cumulants for tensors. And for now, they don't seem very useful. So why would I be interested in these free cumulants? Well, now this becomes a bit more relevant when one tries to now understand what happens in the Radian limit. So for matrices, we have the classical expectations, the classical cumulants, and then the free cumulants, and we'll try to understand what becomes of these, objects in the Radian limit. Now, how to take a Radian limit? Well, one is to be a bit careful with the Radian limit. So first, one chooses a probability measure. So this means that, one is to identify, as a function of the particular probability measure I chose, one is to find scalings, appropriate scalings with n of my classical cumulants, such that a limit when n goes to infinity exists. So, this, for certain choices of probability measures, I will have here scalings which will arise, which will make that in the larger limit, this ratio goes to some finite number, And this particular limit depends on the details of the probability measure, this little phi of sigma is the limit value of my classical cumulant. Now, well, then I can just use my relation between expectations and, classical cumulants, but I need to rescale my expectations with this appropriate scaling. So if I look at rescaled expectations, well, these are a sum of all possible ways to build, to have here products of classical cumulants between various, subsets of these invariants. Now you see that as a function of my scaling factors here, I have here a natural scaling factor for each cumulant, and then I have prefactors here, which see the factor, you see the size n of the matrix. So these prefactors, in the larger limit, some of them will go to 0, essentially, and some of them, will not go to 0. So the question is, which of the terms survive in this sum? And it turns out that if essentially this scaling factor here is strictly subadditive of connected component, so meaning that this factor here, it's the sum of the scaling for each individual invariant is larger than the scaling of the union of the invariants. So if this guy is strictly subadditive on connected components, then it means that among all the possible partitions, one will dominate. And namely, it's the one on each invariant goes individually. So this means that the expectation will be factor as the product of cumulants, classical cumulants. So in the larger limit, there is a risk, as a function of the scalings I have here, that this relation between classical expectations and classical cumulants trivializes, and they just have a product of 6. So this is not very interesting, and one cannot build much on a relation which is completely factor. I mean, this has, this factorization has several effects. One of them is that all the asymptotic information is captured by these cumulants for connected invariants. Fine. However, the reverse is that one needs to go a bit deeper and needs to look for interesting moment cumulants relations, because these ones are just trivialized. So whenever 6 factor, one needs to be a bit, one needs to dig a bit deeper. So what choice of scaling should we pick? So we will pick a case of the choice of scaling, and if you want a natural choice of scaling, we'll look at all the measures which reproduce in the larger limit the Gaussian scaling. So I'll assume that this scaling is the Gaussian scaling. However, I'll make no assumption on the asymptotic value of this classical, this scaled classical cumulant. So with this in mind, one looks at the class of measures and want to understand, okay, do I have, for instance, good observables in the larger limit? Do I have factorization in the larger limit, and so on and so forth? And the message is the following. Well, one can compute, in fact, this scaling for a Gaussian, the Gaussian scaling. So this is just a matter of scaling. It has nothing to do with the particular values, of my asymptotic cumulants. It's just a matter of scaling. So I can compute this asymptotic scaling. And essentially, the message is that this scaling, I mean, it depends on the graph, and it is essentially leading order if my graph is melonic. And if I restrict to melonic graph, this scaling is strictly subadditive. So I will indeed have factorization if I restrict to the melonic family. So at leading order, the leading invariants are always the melonic invariants. And for the melonic invariants, this Gaussian scaling is factor. As a small note, in dimension 2, so for matrices, all the invariants are melonic, because you see, I build these invariants by essentially iterative insertions, and in dimension 2, the only observables are cycles, which I can build by iterative insertions too, So in fact, in dimension 2, so for matrices, I always have factorization, and my scaling is strictly subadditive. For tensors, I mean, this happens for the melonic graphs. I don't know about the rest of the graphs. So in particular, for matrices, I am forced to go and search for non-trivial moments cumulants relations because of the factorization. I have that these expectation factors in terms of the classical cumulant, so that's not a good one. And also, at leading order for tensors, I just deal with melons, and for melons, this, the measure of the expectation factors too. Okay. So I need to dig deeper and find the non-trivial moments cumulants relation. No? Okay. So, I mean, as we said,
Rasman,
yes.
Can I ask you a question? How many more slides do you have? Because we're already a bit over time.
I have a total of 3 slides.
3 more slides. Okay, okay. Then let's see everything. Sorry.
Yes.
Yes.
Yes. So, I mean, first of all, because at leading order, we have to deal with these Meloni graphs. Well, it turns out that the Meloni graphs can be organized in a lattice. So for every Meloni graph, I can have a lattice of melons, which are obtained essentially by performing flip moves on melons. So what is the flip move? Well, in a melon, I take a pair of edges, which disconnect my graph, for instance, these two, and I cut them and I reconnect in the only other possible way with respect to the color. So if I take these two guys and I cut them, I get this drawing here. No? Or I can cut these two guys here and I get the drawing here and so on. So this gives me a partial ordering between melons, which tells me that, you know, a melon is smaller than another melon if it can be obtained by a sequence of flips. And if you look here, you know, I drew all the possible melons which are smaller than this one. So I start from here and I cut this kind of edges, you know, which disconnect the graph and I reconnect them in the other way. And this creates a lattice because, well, I start from this guy, I have various guys in the middle, but the smallest possible graph at the end, it's always this configuration. So this is a lattice, you know, for every melon, I have a lattice, you know, of graphs. And in fact, one can prove that this lattice is isomorphic to a particular sublattice of a default Cartesian product of non-crossing, you know, partitions. So this is a known lattice of a known Möbius function. Why is this useful? Is because this lattice allows me to write moments cumulus relations for tensors for melonic invariants in the following manner. So, you know, in this lattice of melons, you know, I can write, you know, I can, you know, rescale my invariants, take the larger limits, and find the relation between the classical cumulants and the free cumulants. And it turns out that, you know, in this larger limit, the free cumulants, you know, the rescaled classical cumulants become the asymptotic moments, and the rescaled free cumulants are the asymptotic cumulants. So as advertised, I have a good starting point now, a non-trivial moments cumulants relations, and I can try to understand, you know, what's the ab initio, you know, definition of these limit objects. No? Okay. So, you know, if you want to say more details about this, you can go back at Lucas. Now, however, you know, there is a slight point, you know, and namely related to this factorization. So as I said, I have factorization of observable or strict subadditivity for melonic observables. This covers all the observables for matrices, but what happens for tensors? And it turns out that for tensors, the situation is a bit more complicated because in fact, whereas for matrices, the Gaussian scale is strictly subadditive, for tensors, it is not. So if I look, I mean, you know, this holds for Meloni graphs, but if I take an arbitrary graph, you know, big enough, then typically factorization will not hold. And the cumulant, you know, corresponding to a disconnected invariant sigma sigma will actually be larger in scaling than the product of cumulants. So this larger factorization in the case of tensors fails for large observables. So the message is that, you know, contrary to matrices, for tensors, not all the asymptotic information is captured by the classical cumulants. And in particular, you know, for non-melonic observables, one needs to be a bit careful. You know, it's not enough to look at these asymptotic relations between free cumulants and classical cumulants. Okay, so as promised, you know, I reached my conclusions. So I, you know, hope I, you know, managed to perceive that, you know, tensors are an interesting topic. And what we've seen today, it's first some classical results that, you know, this random tensors, I mean, tensors require many invariants to be described as a full zoology of invariants, you know, to be studied. They exhibit a large n limit, which is a bit different from the one of random matrices. They are useful as generators of random discrete geometries. And now more recently, in our attempts to try to generalize free probability to random tensors, we found out new asymptotic relations between asymptotic moments and free cumulants at leading order, but just for a subclasses of invariants, these melonic invariants. However, contrary to matrices, this factorization does not hold, you know, for arbitrary invariants. So, well, what I can only promise, you know, that from now on we'll see many other new things to come, you know, in this study of, you know, the large n theory, you know, of random tensors. Okay, so this is everything I had to say.
Yeah, great. Thanks a lot, Razvan. A very nice talk, very interesting. Okay, do we have questions or comments from the audience? Just, yeah, Kurush, please.
Hi, thank you. It was nice. Does it make sense to ask for same spectrum of different cumulants in this context? Like you have free cumulants, Boolean cumulants. Can you ask such questions, or how would this enter these different lattices that are available in the
So
usual setup?
So the one thing which is a bit, interesting is that, I mean, a priori, you need to define an appropriate notion of cumulant, and then you need to find a good lattice. And I mean, a priori is not obvious, that you can always find the lattice, associated with some notion of cumulant. So what is a bit interesting in this is that if you go to the larger limit, you select the subclass of observables, these melons observables, which actually have a lattice associated to them, which, a priori, it was not obvious you will find one. And this lattice allows you to write these relations for these subclasses. However, for other classes of observables, it's not clear what, I mean, you can always try to order graphs by, to say, okay, I have a graph which I can order by these partial orders, but it's not obvious if I will have a well-known lattice if I look at more general graphs than this melon, So in principle, defining free cumulants for something else than melons, it is, not obvious that you'd have a useful notion. So it's a bit of a, you need to find also an appropriate lattice there.
On this lattice structure that you described, it looked like, is there sort of a Hopf algebra structure there, something that allows us to decompose this from a graph theoretic point of view? You could think about the incidence Hopf algebra.
You want to go the other way around. You want to start from here and start to say I can grow this like that, or grow it in the other way. It's a kind of a Hopf algebraic thing. I can insert here this thing, and I grow a bit my thing, and I insert it there and grow a bit my other thing.
Like a Preely structure, right? Yes, so something like this.
Maybe it's possible, yes. So it's true that I didn't think of it like this. I mean, typically, my way, when you have algebra graphs, you insert things. So my way to see this lattice is to start from the big melon and start cutting things. So I go a bit the other way, and you would go by inserting stuff. But maybe it would be interesting if it's a way to generate it the other way around.
In work with Loic, Joachim Koch, and Frédéric Patras, we did this on non-crossing partitions. We have two different Hopf algebras that sort of reflects the fact that you can really insert these blocks into each other, and there's a different structure there. This was quite interesting.
Because it was a bit too technical, I didn't give the formulation in terms of permutations and so on. But you can see this lattice, the product of lattices on non-crossing partitions is doing something very precise on permutations. You insert stuff in cycles, you do something and so on. So it's possible that at the level of permutation, this insertion to very nicely be able to write it in terms of algebra. So that's very possible, actually.
Okay.
The level of the graphs is maybe a bit more difficult to see, but in the encoding and permutations, it's clear stuff. You insert cycles into things without crossing stuff and so on. So it's very, very close to the non-crossing partitions. So if you have a Hopf algebra generating non-crossing partitions, this should be a generalization of that.
Nice. Thank you. Thank you very much.
Okay, are there further questions, comments? I have a quick question. So you mentioned a lot of interesting motivations for this. Yes, so you had the general relativity, and then random geometries, then the birds, and so on. So what's your main interest, or what's your door here to this?
Okay, so unfortunately, I used to be young. I'm not so young anymore. So when I was very young, I was very motivated by this business with the quantum gravity stuff. So this is why I maintain it here. It reminds me of the time when I was young and naive. The whole story is that, it's very nice to try to do models of quantum gravity, but it typically fails. And I would say that, I have shifted a bit my interest since then. So another motivation to look at these things is to consider these models of field theory with tensors, which are not necessarily directly related to quantum gravity. The interest of looking at at those models is that it allows you to study things like, for instance, strong interacting quantum field theories in a certain regime. And you can hope to be able to solve a bit better these strong interacting regimes than you do it in the usual cases. And indeed, we had some, I would say, interesting results in these strongly interacting, the approach to strongly interacting field theories using, tensor field theories. And this is where I've been, I found my motivation mostly in the, lately, more than in this quantum gravity thing. So this quantum gravity is very nice, but it's for younger people. So.
Okay. Yeah, thanks. Dominic is there. Dominic, do you have a question?
Hello. Yes, I have maybe a young and naive question about the physics in the beginning of the talk.
Yes.
What is the mass of a black hole whose Schwarzschild radius is equal to the Planck constant? Roughly.
I never looked at this.
Okay.
So the mass you should take this Planck, so 10 to the minus
Yeah,
30,
yeah, yeah.
multiply by g c square and divide by g, the
Yeah.
Newton coupling.
Yeah,
And this
yeah.
will give you the mass here. Oh, sorry. Oh. I mean, I never look at orders of magnitude. So let's see. So 10 to the minus 35 meters. I mean, I'm not very sure about the Newton's constant, how small it is. I mean, so this g is typically very small here.
Yeah, yeah, yeah. Okay. Newton's
So I mean, c
constant,
square is
yes.
big, g is small, but RS, I mean, the Planck scale is also relatively small. So yeah,
Yeah,
good
yeah,
question.
yeah. And another question which is a bit related, if a black hole is very, very small, it should evaporate quickly, if we believe Hawking. So when you approach this mass of the smallest possible black hole, what happens?
So, I mean, that is a very good question. So that is part of the things which we don't really know. No? So, I mean, the statement is
Yeah.
the following. We know that as long as this Compton, I mean, typically the regime we are in is that the Compton length is much bigger than this Schwarzschild black hole. So typically
Okay.
you test, you measure what happens to your photon at scales which are very quantum and not very GR, not very general relativity, because,
Okay.
the radius is much smaller there. But of course, the point is that, at some point when they become of the same order of magnitude, then you should really start to worry about these aspects. Is it really a black hole or not? Is it, then does it evaporate or not? Does it leave a remnant or not? And all that thing. And this is, I mean, where you would like to be able to describe such physics by this kind of, theory here. And as I was saying, this is something which people don't really know how to do very well. And these are many, approaches come about. And some of them are crazier than others. And this, discrete geometry is only half crazy. There are crazier things than this.
Okay. Thank you.
All right, then I think that was it for the comments and questions. Then thanks again, last one. Very nice talk. I hope you all